Hey kiddos, happy lesson number 8. Good to see you. Today we're going to continue our study of the nucleus and nuclear physics. So let's take a look at our goals for today. We're going to debrief that Pentium lab, see if any of you came up with a relationship between remaining parent nuclei and half-life. Then we're going to model nuclear decay and half-life to formalize those relationships. Talk about things like decay constant and nuclear activity. And then we're going to discuss the energy released in fission and fusion reactions. And we'll actually talk about Einstein's E equals mc squared today. All right, let's get going. All right. So if you completed the Pentium activity, you would have gotten a line of best fit that was a exponential decay, probably an exponential decay in terms of nuclear half-lives, and it probably looked a little bit like this. All right. So what you would have noticed is that you would start off with all of your parent nuclei, and we label parent nuclei when we're talking about half-lives and decay as n sub naught, right? Like the original number of parent nuclei. And then over time, after one half-life, how many about were left over? About half the original amount. And then after another half-life, how much was left over? About half of that, a quarter. And then after another half-life, how much was left? Another half of that, an eighth. All right. Hopefully I paused in time so I didn't just sneeze in your ear. All right, so let us see if we can come up with a relationship for that. All right, if we want to know how many nuclei, parent nuclei, are left undecayed after however many half-lives, we could say n naught divided by 2. We could say, actually, the number of original nuclei times 1/2, right? And after no half-lives, we would just end up with the number of original parent nuclei. After one half-life, we could take it to the power of 1, and we'd end up with n naught over 2. After 2 half-lives, we'd have n naught times 1/4, and after 3 half-lives, we'd end up with n naught over 8. All right, so that works out. So if we write this equation, we can figure out the remaining number of parent nuclei. We can put a little n for number of half-lives or something along those lines. And soon enough, we'll come up with a relationship for the decay over time. So this is looking at the percent of remaining parent isotopes versus the number of half-lives. But what if we just look over time? Okay. One definition that I need to define before we move on is the nuclear activity. So nuclear activity is the number of nuclei decays per second. Right, so decays per second would be a good unit, but decays per second are actually named after Henri Becquerel, one of the researchers that worked with the Curies on nuclear decay, and it is abbreviated with a capital B, lowercase q. Right, and this is called the Becquerel. Okay, so we can say activity is the number of decays per second. Activity is abbreviated with a capital A in units of Becquerel, or decays per second. All right. All right, let's define ourselves a nuclear decay law. So now we're looking at undecayed or parent nucleus as a function of time. So the number of nuclei that will decay per second is proportional to the number of atoms present that have not yet decayed. So to write that in symbol form, the number of nuclei that will decay per second, right, the activity, is proportional to the number of atoms present that have not yet decayed. It's a number of remaining parent nuclei. Okay, activity. And then undecayed nuclei. So to make that an equality, we just need a constant in there. I know. We're going to use the Greek letter lambda. And the Greek letter lambda is the symbol for the decay constant. And the decay constant is in a unit of 1 over time. So it could be, it's time to the negative 1 power, could be in units of seconds to the negative 1 power, hours to the negative 1 power, years. Doesn't super duper matter, just as long as you know what those units are, what unit of time you're talking about. Okay, so activity is proportional to the number of undecayed nuclei, where there's a decay constant in 1 over, that's 1 over time. Okay, so we could also write this as, what about the original activity is equal to the decay constant times the number of original number of parent nuclei. Okay. So, all right, so now that we've got those terms defined, we can take a look at this graph up here and we can write an equation that models that decay, right? So our number of undecayed nuclei equal our original number of parent nuclei times E, and it's a decay, right? So it'll be a negative exponent. The decay constant will be the constant and then times time. All right, similarly, we could write this in terms of activity, right? Since the activity is proportional to the number of undecayed nuclei, we could write just a very similar equation for activity. Activity is equal to the original activity times E to the negative decay constant times time. And then if we know that the original activity is equal to the decay constant times the original number of nuclei, we can plug that in right here, and we can get activity is equal to lambda and not e to the negative lambda t. So these are our two equations that we can use. And then this guy is kind of one of our starting places here. All right. So as we're looking at this, we noticed that it took every time there was a half-life, right, in our activity, every time we shook up our container of pennies or M&Ms or whatever and dumped them on the table, that represented a half-life. And statistically, about half of the nuclei decayed each time, right? So at a half-life, right, a half-life is the time it takes for half of a parent nucleus to decay. So half-life is abbreviated often T1/2. And at a half-life, the number of undecayed nuclei equals the original number divided by 2. So just like we were talking about on a previous slide. So if we use the equation that we just came up with, n equals n naught e to the negative lambda t, if we take this and plug it in for the number after one half-life, n is the maximum number of a parent nucleus, or the original number divided by 2, and that is equal to n naught e to the negative lambda t. And what we're trying to figure out here is what is the half-life? How long is a half-life for a specific nucleus? And so we can, this t, right, if the original number of nuclei is divided by 2, this t is T1/2, and we need to work on solving that. So here we've got these n naughts cancel, okay, and solving for T1/2 up here, we get half-life is equal to the natural log of 2 over lambda, which is 0.693 over that decay constant. Okay, so if you're asked to solve for half-life, all you really need is the decay constant if you've got this relationship here. But where it comes from is it comes from this base equation. All right, so let's do a quick example here. Radium-226 emits alpha particles. The decay constant is 1.35 times 10 to the minus 11 inverse seconds. What mass of radium-226 is needed to give an activity of 2200 becquerel? Okay, remember becquerel are decays per second. All right, so let's see here. We're looking for mass, but we don't really have any of our equations that we've discussed recently that have mass in them.